Today, we will explore one of the timeless challenges in mechanics, the problem of fastest descent, and in doing so, delve into the principle of least action which we accept in modern times. We'll approach this problem by tracing its historical significance and understanding its profound connection to the behavior of light, which follows similar philosophy governed by a different set of rules. This journey promises to be very fascinating and insightful as we uncover the principle of least action and its historical development. Let's get started. I'm Dr. Shyamkant Anwane, associated with Sri Shivaji Education Society, Amravati Science College, Nagpur, and involved in this profession from past 25 years. The problem of fastest descent has evoked our interest since a very long time. You can observe on your screen the birth years of various scientists. Fermat was born in 1607, Maupertuis in 1698, Euler in 1707, and Lagrange in 1736, followed by Hamiltonian, whose principle we accept at present time in learning mechanics. These are the birth years of various scientists on the timeline. Pierre de Fermat, a French mathematician, was the first person on this planet who got entangled with the issue of fastest descent. If you take any kid to any scientific display wherein the fastest descent is displayed, you along with the kid will be entangled with what is happening. Maupertuis was also a French mathematician and a philosopher who came after Fermat. Leonhard Euler was a Swiss mathematician, physicist, astronomer, geographer, logician, and an engineer who found the studies of graph theory and topology and made pioneering and influential discoveries in many other branches of mathematics that includes analytic number theory, complex analysis, and infinitesimal calculus. Then we are going to refer the work of Joseph Louis Lagrange, an Italian mathematician, physicist, astronomer, and later neutralized French. He made significant contributions to the field of analysis, number theory, and both classical and celestial mechanics. Then we are going to refer the work of Sir William Hamilton, who was an Irish mathematician, physicist, and astronomer. We are going to conclude our discussion with Hamiltonian principle. He was professor of astronomy at Trinity College, Dublin. If you want to slide a mass from point A to point B, what shape of ramp would get it there the fastest? This is known as the problem of fastest descent. At the first glance, the common sense might suggest taking the shortest path, that is, a straight line from A to B. However, if the ramp dips downward initially, the mass accelerates more quickly. If the ramp dips downward initially, the mass accelerates more quickly, achieving a higher speed early, even though the path is slightly longer as you can see on your screen. But the increased speed allows it to reach the descent destination faster. The question then becomes what ramp shape strikes the perfect balance between acceleration and path length to minimize the travel time. Let us see the descent. So longer path but sliding a bit faster than earlier case. In 1968, Galileo proposed that arc of a circle was a solution, demonstrating that it was the faster than any polygonal path. But was it the fastest possible? Let us see the descent once. Nearly 60 years later, in June 1696, Johann Bernoulli issued this problem as a challenge to the world's top mathematicians. Known for his competitive nature, Bernoulli likely wanted to showcase his own brilliance. He gave everyone 6 months to submit the solution, but none were received within the initial deadline. Leibniz, a friend of Bernoulli, persuaded him to extend the deadline to give more people, particularly foreign mathematicians, a chance to participate in this quest. Johann likely had Isaac Newton in his mind, as Newton was regarded as the foremost mathematician of that time. By then, however, Newton was no longer actively engaged in mathematics or physics, having taken up a high-ranking government position as a warden of the mint. One fine evening of January 1697, Newton returned home after a long day of work to find Bernoulli's challenge awaiting him. Though initially annoyed, remarking, "I do not love to be done by and teased by foreigners about mathematical things," Newton couldn't resist to solve the problem. It is interesting to note that overnight he solved the problem, a task that had taken Bernoulli 2 weeks. Newton then submitted his solution anonymously to the Journal of Philosophical Transactions. But Bernoulli could recognize the work of Newton. In physics and mathematics, Brachistochrone curve, a curve of fastest descent, is the one lying on the plane between a point A and a lower point B, where B is not directly below A, on which a bead slides frictionlessly under the influence of uniform gravitational field to a given end point in the shortest time. The problem was posed by Bernoulli, as I said earlier. You can see the descent along a linear track for a particular problem in 0.668 seconds. The second descent example is for circle, that is in green color. You can observe a bead descending under a gravitational field in 0.58 seconds on circular track, and you can compare with the linear. Then you can observe the descent along a parabolic path in 0.571 seconds. You can observe this to be yet smaller as compared to circle. And finally, and most interestingly, along a cycloid, it takes the least time, that is 0.566 seconds. We shall try to see the same thing at one time. Here, I have adjusted this time of 566 milliseconds to some sizable time that we can observe on our screen by a multiplying factor, and we can see together the descent. And here you can observe that on cycloid path the descent is fastest. Now the question is, what is cycloid? Cycloid is the curve described by a point on the circumference of a circle as it rolls without slipping on the straight line. The cycloid is extended if the point is outside the circle and contracted if the point is inside. Here we are in the Maple worksheet of a cycloid. A cycloid is the path that is traced out by a point on the circumference of a circle as it rolls along a straight line without slipping or sliding. It can be expressed by a pair of equations. X of theta is equal to r times theta minus sine of theta, and y of theta is equal to r times 1 minus cos of theta. So here on the screen you can observe the cycloid motion. Now I am going to play this animation for you, wherein you can observe the point on a circle when it is rolled, not slided, traces some trajectory that is appearing on your screen in blue color is cycloid. When you change r from unity to some different value, you can observe what kind of effect that comes into picture. So as r changes, the descriptions on y-axis changes. However, when L changes, you can observe what is happening. I have to pause this and then change the value of L, and you can see the effect. Prima facie, we are not interested in other cycloid motion parts. I'll set this L equal to unity and this R also equal to unity, and the blue color trajectory that is created is cycloid. The balls rolling under uniform gravity without friction on a cycloid, black color you can observe, and straight lines with various gradients. It demonstrates that the ball on the curve always beats the balls traveling in straight line path to the intersection point of the curve. Now let us deal with how light travels between two mediums. Imagine that this very line is a boundary line between two medium. The upper medium is a denser medium and lower medium is a rarer medium. So denser medium having density mu1 greater than mu2. And let us suppose that light is incident like this at an angle theta1 with the normal. So when light travels from denser to rarer, it bends away from the axis, normal axis. So obviously theta 2 is greater than theta 1. The opposite is situation when it travels from rarer medium to denser medium. The another issue of light travel across the medium, not exactly across the medium, when it is reflected, the incident ray makes an angle theta I with the normal to the surface from which it is reflected. and theta r is the angle made by reflected ray. So theta I is always equal to theta r. Here we have a situation. This line represents interface. The upper region is having a rare density. The lower region, which is in blue shade, is a bit denser as compared to the upper medium. The refractive index of upper region is N1, which is governed by the density of the medium, and N2 is the refractive index of lower medium. In this situation, the light is incident at an angle theta 1 with the normal, and you can observe that when light is refracted across the interface, it bends towards normal because the medium is denser. So here we are going to establish Snell's law. Snell's law is a formula that is used to describe the relationship of the angles of incidence and refraction when referring to light or other waves passing through the boundary between two different isotropic media such as water, glass, air, etc. In optics, the law is used in a ray tracing to compute the angles of incidence or refraction, and in experimental optics used to find the refractive index of the material. Refraction of light at the interface between two media of different refractive indices where N2 is greater than N1 or situation. Since the Snell's law offers us sine of theta 1 upon sine of theta 2 is equal to N2 upon N1. You can pick up the ratio as a relative refractive index N to 1. Now, later on, it was found that it is exactly equal to the ratio of velocity of light in the first medium to velocity of light in the second medium. Now, since the velocity is lower in the second medium, that is V2 is less than V1, the angle of refraction theta 2 is less than the angle of incidence theta 1. That is, the ray is in the higher index medium close to the normal. The law states that for given pair of media, the ratio of sines of the angles of incidence theta 1 and angle of refraction theta 2 is equal to the refractive index of the second medium with regard to the first medium, that is n to 1, which is equal to the ratio of refractive indices n2 upon n1 of the two media. Now, you can observe here that when the observer is trying to heat a fish beneath water, he observes that the fish is having this apparent position. Fish appears here. So he'll try to hit the fish in this fashion and he will miss because of refractive index of the water. The fish is actually here but appearing at this place. This is an educational illustration showing a man aiming an arrow at a fish underwater. This includes the effect of light refraction, highlighting the apparent versus actual position of the fish. The law follows from the Fermat's principle of least time, which in turn follows from the propagation of light as waves we are going to discuss in the coming slides. We are in the Maple worksheet where we can define the refractive index N1 from the upper region and refractive index for the lower region N2, which is 1.333. Here we can set up the value, we can set up the angle of incidence, and for different materials here you can observe the index of refraction. Now you can see if N1 is equal to N2, then light will not get refracted because there's no change in medium. There's no change in the refractive index of the medium. There is no change in the density of the medium. But when the lower region has higher and higher refractive index as compared to unity for air, you can observe the bending of light going closer and closer and closer to the normal axis as per the Snell's law, and it becomes very close for 2.5, which is for the case of diamond 2.42. Here you can change the angle of incidence. Here it is 60°. Now I am going to reduce this and you can observe the effect. So this is wonderful demonstration through a Maple worksheet. The Fermat's principle states that light travels between 2 points in a way that minimizes the time it takes to travel. So minimization of time of travel is the whole story that is of interest and importance. Fermat's principle, also known as the principle of least time, is the link between ray optics and the wave optics. Fermat's principle states that the path taken by a ray between two given points is the path that can be traveled in the least time. I want to highlight this. It is the path that can be traveled in the least time. So we are going to work out certain things based on this underlying principle. If you use that principle of least time, you can explain everything that was known about light at the time of Fermat. It's the first time, I guess, that anyone shows that nature obeys optimization principle, that nature does the best possible thing. In case of light, it takes shortest possible time. Now in this situation, let us suppose that we have 2 points. For example, this is a point A and the another one is point B. The situation is that light has to travel from A to B. And now let us suppose that light is traveling this way from A to the boundary, and then it reaches to B in this way. Now you can work out the time of flight of light for all such paths. The another you can work out like this. The one with red color, this path, which actually light travels, will take least time. It will be traveling in the least time as compared to all possible combinations for light to travel from medium 1 to medium 2 via different points on interface. So this is the situation in which it takes least time for light to travel from A to B. Here I want to highlight that this very path traced by the light takes least time, and here you can observe that this path will be something like this here, and for which the least time is recorded. Now here you can observe the interface between two regions of different refractive index, and here in this diagram this vertical line is the interface between two regions. You can consider this region on left hand side as air medium, wherein the velocity of light you can call say c, and velocity of light in this region you can call v. Likewise, the basic equation that we have started with is sine of theta 1 upon sine of theta 2 is equal to n2 upon n1 is equal to v1 upon v2. So this can be rearranged as sine of theta 1 upon v1 is equal to sine of theta 2 upon v2, and we can go on extending this on right hand side if we have number of such regions having different velocities and different angles. Similarly, we can modify this equation as index for region 1 into sine of theta 1 is equal to index for region 2 into sine of theta 2. For wave optics and ray optics, it holds true. Now we are going to club how light travels with the descent and fastest descent. Johan's brother Jakob showed how second differentials can be used to obtain the condition for least time. A modern version of proof I'm going to discuss here. If we make a negligible deviation from the path of least time, then the differential triangle formed by the displacement along the path and the horizontal and vertical displacement. Let us see how it goes. Now, here we have two regions. I can call this as region 1 and the lower one as region 2, and some refraction is taking place, which is shown up here. Now you can consider the displacement ds, dx, dy, and we can write this in the form of Pythagorean equation ds square is equal to dx square plus dy square. Taking differentiation on both sides, ds square will be 2ds into second order derivative equal to 2dx into second order derivative dx2, and there's no change in y we are considering. So d2s will be equal to dx upon ds. So I'm cancelling this 2 and taking this ds here in the denominator. This offers us v dt square. So I'm writing second order of displacement equal to velocity into second order of time differentiation into dx by ds into d2x. So taking v on right hand side, we get d2t is equal to 1 by v dx by ds into d2x. So we can extend this equation for region 1 and region 2, and we can take difference of that. And this has to be least, this has to be minimized. That offers us this very condition. Now, the simplified version of that condition you can observe here is 1 upon V2 equal to dx2, that is for second region, divided by ds2 equal to 1 upon V1 into dx1 upon ds1. So here you can identify ds1 as this part and ds2 as this part. The second order differentials you can identify d2s1 and d2s2. We are going to explore this condition for least time in our equations. Here you can observe a right angled triangle which fits into the geometry that we are going to handle. This side is dx, this one is dy, and this is ds. Now it fits into our geometry wherein this side is dx, this one is dy 1, and this one is ds1. And to the normal we are having the angle made by the incident ray theta 1, which reflects in our figure here. And note that sine of theta is front upon hypotenuse. So you can observe this ds1 here and dx1 here. So dx1 upon ds1 will be sine of theta. So here you have to relate that, and consecutively you have to go on doing that. So sine theta 1 is front side upon hypotenuse, and you can replace the last derived equation, which was the condition for least time, to an equation which is a bit familiar to us in the form of Snell's law. So the another great mathematician enters in our story at this point, and this is Pierre Fermat. He mostly worked in pure mathematics, but at one point he got interested in the question of why does light obeys this principle of refraction? And he thought maybe the hero of Alexandria was on the right track, but it's not distance that is being minimized, but rather time. But to see if this was true for refraction, it would have been very difficult to explain the concept of refraction. He would have to work out every possible path light could take by varying the point where it intersects the boundary and compute time for each, and then show that light takes the path for which the total travel time is shortest. 5 years later, he tries to solve it, and then he does solve it. He shows that the Snell's law actually pops out as minimizing path for light. You know, under these conditions, for moving from one medium with speed of light to another medium with lesser speed of light if it is a denser medium. And then the constant n, well, that is equal to speed of light in the first medium divided by speed of light in the second medium, that we are learning as Snell's law. So if you use the principle of least time, you can explain everything that was known about light at the time of Fermat. It's the first time, as far as we understand here, that one shows that nature obeys optimization principle, that nature does the best possible thing, and in this case light takes the shortest possible time. Now Bernoulli knew about the Fermat's principle of least time, and he thought he could use it to solve this problem of fastest descent. So he converted the problem from a mechanics problem about a particle sliding down along a curve to the problem about optics. Instead of mass that's accelerated by gravity, he imagined that a ray of light that would go faster and faster as it went into the layers of less and less density. Here you can observe the density of the layers is decreasing as one travels down, and when the light enters into it, as the density decreases, its speed goes on increasing continuously, and this is comparable to the problem where mass is falling under gravity. And if you make the layers thinner and thinner, where Snell's law is obeyed at each interface, you eventually get a continuous curve. Now, the question is, how would speed of light change from one layer to the next so that accurately we can model the falling object? You try to solve the problem by thinking, if the particle has fallen from A to B, it's going to picking up kinetic energy as it's going faster and faster as it slides down the curve, and it's converting the loss in potential energy into kinetic energy. And if you write down the conservation of energy for that particle, that relationship will be able to tell you something about velocity gained by the particle at any time having fallen a distance, something say y from the top. Here we are tracking the problem of Bernoulli's solution, wherein we are talking about the distance of the particle from the horizontal. So we are interested in this vertical distance y. So let us slide a particle from A to B, and here at any point of time you can find out the distance y from the top. So if you like to find it at some time, intermediate time, you can define y of t, and at that time what is the distance of the particle from uh, this very horizontal. I am talking about the vertical distance, and we are here dealing with the total energy is equal to potential energy plus kinetic energy, and nothing plays in between except gravity, and the slide is frictionless. So the total energy being conserved we are considering in the sense that neither added nor subtracted, so it remains constant, and potential energy plus kinetic energy is not undergoing any rise or fall, so that makes equal to 0. So potential energy is equal to minus times kinetic energy, or you can write mgy, that is potential energy in the gravitational field, plus kinetic energy of the sliding object m 1 by 2 mv square. And here you can ignore the mass because it doesn't depend on that mass. That's very clear to us from the famous experiment by Galileo from Leaning Tower of Pisa. And here we can rewrite this equation as v square equal to minus 2gy, or you can conclude v is directly proportional to square root of y. Now, its velocity squared will be proportional to y, which is height from the top. So the velocity goes like the square root of y, and that would be the shortest like now see here, this is Snell's law, sine of theta 1 upon v1 equal to sine of theta 2 upon v2 and so on. Now it would be sort of like saying, imagine the light moving in a way where instead of constant speed of light, the speed of light is proportional to the distance from the top, as we have worked out in the earlier slide. And now let's zoom in and look at a single interface as appearing on your screen. We can plunge in our expression for speed of light in each layer into Snell's law and find that the sine of the first angle divided by the square root of y for the first layer is equal to sine of second angle divided by square root of y for the second layer. And now here's the key insight. Snell's law also holds for the next layer, and there the ingoing angle is simply theta 2. So we can go on expanding this for the next multiple layers, making it a continuous issue. So this is equal to sine of the third angle divided by the square root of y3. And the same goes for the next layer and the next layer and so on. In other words, this ratio must be equal to some constant, call it like k. And this equation Bernoulli immediately recognized is the equation of cycloid, that the path traced out by a point attached to a rim of a rolling wheel. This is also known as Brachistochrone curve from Greek for the shortest time. And the astonishing solution is that the fastest way to get from A to B is to follow the arc of cycloid, not a circle. Now, this curve also has another surprising property. No matter where I release the mass from, it always reaches the end at the same point of time you can observe on your screen. For this reason, it's also known as Tautochrone curve from the Greek meaning for the same time. Upon finding this solution, Bernoulli wrote, "In this way, I have solved at one stroke two important problems, an optical and a mechanical one, and have achieved more than I demanded from others." I have shown that the two problems taken from entirely separate fields of mathematics have the same character. Around 40 years later, one of his students, Maupertuis, Pierre Louis de Maupertuis, also studied the behavior of light and particles. And he noticed that there are cases where the two behave very similarly. This made him think, what if Fermat's principle of least time wasn't the most fundamental? Meaning by, why should nature care about minimizing time? Maybe there is more fundamental quantity being minimized, one of that doesn't does not only govern light but also particles. So in the year 1940, he proposed a new quantity which he called action. This is the first reference of action. It is mass times velocity times distance. His thinking went something like, the farther something travels, the greater action. Faster it goes, the greater action. And if it's particle, then it can be more massive and the greater action. If there are multiple segments to the journey, then the total action is just sum of mass times velocity times distance for each segment. To see the principle in action, here we shall discuss one example wherein there is no friction and no losses. In classical mechanics, Maupertuis' principle states that the path followed by a physical system is one of the least length with suitable interpretation of path and length. It is the special case of more generally stated principle of least action. Actually, it is the beginning of development of the principle of least action. Maupertuis' principle states that the true path of a system is described by the generalized coordinates, say q, between two specified states q1 and q2 is minimum, or a saddle point of abbreviated action function. Now, by definition, the action S0 is equal to mass into velocity into distance. If you have more segments, then it will be summation of all those. So here the parameter of action depends on farther it goes, action is more, that is distance. Faster it goes, the action is greater, that is velocity. Massive it is, then the action is greater. Now here we shall elaborate this to a better extent. This S0 can be written as momentum into distance because mass into velocity is momentum. Now S0 depends on Q of t, that is equal to summation of all momentum elements in different segments multiplied by the distance it has traveled. Now here we shall discuss a specific case, a specific example wherein we shall consider a mass of half kg. You can observe a ball of half kg. Let us suppose that it is traveling with speed 3 meter per second over the distance of 6 meters and bounces and pings back, say reflected without losses. So S0, that is action, is equal to mass into velocity into distance, which is summation of mvs. Now we shall go for that animation of bouncing back of this. So half kg multiplied by 3 meter per second multiplied by 6 meters distance it has traveled, and for reflection also without losses, 6 meter distance was traveled. There was no loss of momentum, it was conserved, therefore it is reflected back, pinged back with the same velocity in another direction. Mass remains the same. So this makes 9 plus 9 equal to 18 kg meter square second. This will be the unit of action according to Maupertuis. Now, as against the actual travel of this half kg mass along this red path, you can work out the possible combinations of travel. You can take it from this direct descent to this one, so on and so forth. You can make all possible combinations, and you will be surprised to know that it takes the least action. When it travels along the path, it has actually pinged back, that is the red path. This position of the ball we shall define A. It is traveling along this red trajectory 6 meters distance going to position B, and then from B to C it is again traveling 6 meters distance to reach to position C, you can see. Now the vertical distance between A and B is small b equal to 3, and the horizontal distance between A and B is small a equal to 3 root 3, making our hypotenuse 6. You can verify by Pythagoras theorem. Now in general I am writing A, B, C trajectory, A to B, B to C, for actually that has happened, but I want to generalize that, so I'm using x plus a square plus b square. So this part, and then under root of x minus a square plus b square. Now we shall substitute a equal to 3 root 3 distance and b equal to 3, and we shall calculate what is the value of L, and you can find out it turns out to be 12, which is minimum. So what I have done, I have actually plotted this as a function of x. So here I'm plotting L on y-axis, sorry, x-axis, no, y-axis, and x is being plotted along x-axis. So here, this particular case is having 12, this value. So if you substitute a equal to 3 root 3 in our case, and b equal to 3, which is our case, then L0 is 12 that you can calculate. We have, in earlier slide, we have calculated action, and here we are calculating distance. More distance, more action. Minimum distance will count minimum action. So here you can observe that L, which is function of x, for different x, like you can travel this way, this dotted, I want to show you this, you travel by this path, the distance will be more. You travel by second dotted line path, the distance will be still more. The distance will be minimum 6 plus 6, 12. You can observe here. Now what Maupertuis claimed is that out of all possible trajectories where the ball bounces off the wall, the path it will follow practically is the one that minimizes the action. In the year 1744 he wrote, "This action is the true expense of universe, or you can say nature, where she manages to make this action as small as possible." So what was the response of Maupertuis' revolutionary idea? One of my teachers with whom I discussed this issue, Professor of Mathematics Dr. T.M. Kurde, posed a question in this discussion, whether it is the nature that expends minimum in form of action, or Is it the particle that is smart, that takes a path where the expenses are optimum in terms of action? I am really puzzled who is smart, nature or the moving particle. There was no obvious reason why nature should care about the mass times velocity times the distance. Why that quantity should be minimized. And mathematically, the principle of least action wasn't rigorous either at this point of time in the course of development of this issue. But there was a man who vehemently defended it, and that man was Leonhard Euler. The first thing Euler did was he replaced the sum with an integral, so you could calculate the action while the speed or direction changed continuously. And he used this to find the path of the particle around the central mass like the orbit of a planet around a star. Solving this meant that it was out of every possible path between 2 points, he would have to find the one for which the action was smallest. This is similar to the problem of Fermat, who tried to solve, only now instead of changing one variable, he could have to vary every possible point along the path, which are infinitely many. This was the issue. The principle of least action only worked if the total energy is conserved and the total energy is independent of the path fixed between the starting point and end point. So the action, which was S0, that is equal to mass into velocity into distance in form of summations, was simply expressed as momentum into distance, and then it can be replaced by the integration p into dq, where dq is the variable for distance, generalized variable for distance. You can look for ds also if you like. Fortunately, Euler himself invented a new method. It was chunky and time consuming, but it worked very well. Through this process, he realized that the principle of least action only works if the total energy is conserved, and it is the same for all paths considered. These were the two conditions that Maupertuis didn't realize were necessary for consideration. But Euler was still far from the general proof that would have to wait for another legendary mathematician, Joseph Louis Lagrange. Joseph Louis Lagrange was a shy 19-year-old, mostly self-taught. But despite his age, he was already working at the forefront of mathematics, including with Euler's new method. In 1754, he shared his result with Euler, who replied that Lagrange had extolled the theory to the highest summit of perfection, which caused him the greatest joy. But besides being world-class mathematicians, the two had another thing in common. They were both huge proponents of principle of least action. Just a year after Maupertuis' death, Lagrange could succeed in providing a general proof. Now, I want to explain Lagrange's proof, but don't want to do it the way he did. So instead, we'll go through three steps. First, we'll explain the general proof, rather general approach that Euler explored and Lagrange came up with. Then we'll rewrite the principle into a modern form, and finally we'll apply this mathematics to a simple example to show why it works. So let us get into the intricacies in the modern form. On your screen, you can observe an athlete throwing a shot put. The motion is projectile, everyone knows that. We'll handle the problem from that perspective. Here, we are going to follow Lagrange's intuitive way through three steps. As I said earlier, first we shall deal with the general approach followed by Euler and Lagrange. Then we'll rewrite the principle into the modern form. General approach, then modern form, and then finally we'll apply this to a simple problem, an example which we have seen as a projectile motion. So first, the general approach: if there are infinite possible paths, then how do you find the one with the least action? So well, Lagrange and Euler realized that one can find the minima of a function in the similar way it was proposed by Euler. There you take derivative and set it equal to 0, which even 11th or 12th standard student is knowing these days. And where the slope is horizontal, that must be the minimum. Let us get into the theory of finding minimum of a function for this purpose. Here we shall get into Maple worksheet to clearly understand maxima and minima of function. Here in this worksheet, I shall try to show you graphically how the first derivative and second derivative play a role in showcasing whether the function has maxima or minima and whether it is maxima or minima using second derivative. Now, for this, I am restarting the accumulators of Maple and I am freshly writing this function f equal to x cube plus 4x square plus 2x minus 1. This function I have purposefully selected that possesses a maxima and minima. So in blue color here you can observe the function accepted by Maple. Then f1 I am assigning f suffix 1, I am assigning as first derivative of the function. So here you can see f dash. So that makes a first derivative with respect to x, and it is 3x square plus 8x plus 2. Now from calculus we know that the slope is 0 where the function has maxima or minima. I'll show you graphically later on. And as the line which is tangent to the curve is parallel to x-axis at the point of maxima and minima, we are equating this first order derivative with 0. And then we are solving this quadratic equation this time to find two roots, and you can observe the first root this one and second root this one. We can look for the numerical values of those maxima and minima. Now f suffix 2, f2, that is second order derivative with respect to x, it will be 6x plus 8. So here you can observe, if you again differentiate this first order derivative, it will be 6x plus 8 plus 0. Fine. Now at the point of maxima or minima, which we have found by equating the first order with respect to 0, we can find out the values. If the value is positive, the function has minima, and if the value is negative, the function has maxima. So value of x is different. So at minus 0.2 the function has minima, and at x equal to minus 2.38 the function has maxima. That is what theory says. Now very quickly what we shall do, we shall assign the same function in form of y. Now I want to process it for plotting and do not want to conflict the earlier calculations in Maple. So I have assigned g as function of y, same function, and now I am plotting this in the range minus 4 to 1. So here you can observe that this function has a maxima around at this point and minima around at this point. Now what we shall do, we shall plot this function g and its first derivative together. So here you can observe that the blue color line is our original function and the first derivative is being plotted in red color. So the point where the function has maxima, at this point you can observe the first derivative is 0. Similarly, at this point where the function has minima, the first derivative is 0. Now let us plot three things together. Function in green color, then first order derivative in blue color, and second order derivative in red color this time. So the point where function has maxima, you can observe the cursor, the first order derivative is 0 and second order derivative is negative. Similarly, the function where it has got minima, you can observe the cursor again, the first order derivative blue color line is cutting x axis, so the first order derivative is 0 and second order derivative is positive. So derivative positive, second order derivative positive means the function has minima. So this is a very interesting example. This was the Euler's proposition which we are using in the modern form, and now we shall explore this for minimization of action. So here the first graph I have picked as it is, and we are interested at a point where the function has minimum of a function. So I'm zooming the graph only around those points where the function has minima. You can identify the numerical values of y-axis and x-axis, which is a replica of this point. Now here, the point at which function has minima, you can observe that the tangent line has slope 0. So tangent line is first derivative. We are equating to 0 because the slope is 0. Then if we go little to the left, instead of 0 it will have some negative slope, and if we go to the right a little bit, then it has positive slope. The value of function has not much changed. I mean to say that when we are moving around the x value in the close neighborhood of the point where the function has minima, you can observe the exact minima is having slope 0, and negative slope and positive slope as we go to left hand side and right hand side. So let us move little farther so that you can clearly understand what is happening. And here you can observe that by creating small perturbation along x around the point of minima, you can go towards negative slope or positive slope depending upon whether you are going on left hand side or right hand side. However, the value of the function is not much changed. You can observe that for this particular band of x values, y is not changing much. The laser pointer is indicating the y values. So this is how things are going, and we want to explore this variation for going around a path which is of least action, we want to say. If you took a tiny step to the left or to the right, the value of the function basically does not change much. And similarly, if you have a path of least action, then if you were to change a little bit by, say, by adding a tiny bump here or flattening there, it would just add a tiny to the function eta to our path of least action. Then the action basically doesn't change because we were at really a special point, the path of least action. You add a little bit to the minimal path, but the action is still same. If that is optimal path that has least action, then any other path must have more action. So the counter there is like all of these is first order. So from the actual path you can observe on your screen, we are taking some up and down and flattening and so on. And then you are looking for the linear terms that are proportional to eta, the deviation. Then the first order difference in the action will be zero. And the way you could imagine this, like let's say you are at the bottom of the bowl and you are at the minimum and you make some tiny step away, and we'll call that step eta. If that change would be proportional to eta, you may increase on this side but decrease on another side, and then this would no longer be minimum. So sort of coefficient of eta has to be zero. But since you are at minimum, it kind of goes like a parabola. You can observe the projectile motion. So it can be proportional to eta squared or potentially some higher order term. So there is a tiny deviation in the action, but it's not proportional to eta. So the first order, the change in the action of the minimal path, optimal path, and some trial path is zero. So what you can write is that the action of this trial path minus the action of the true path equal to zero to first order. This is the compact way of writing the principle of least action. So here we shall look at the equations. This is the eta deviation. X of t, which is in the red shade, is the actual path, and q of t, which is in the blue shade, it is the trial path, and eta is the deviation you can observe. So f of x is proportional to eta and eta square, and the principle of least action demands that the difference in the action should be zero, and that is what we are talking about. So with that in hand, let's try to rewrite the principle of least action in its modern form. So the modern form, the principle of least action is the fundamental concept in the Lagrangian mechanics that states that a particle or a body will choose a path that requires least action between 2 points. The Lagrangian is the quantity that is used in this principle, and it is defined as the difference between kinetic energy and potential energy. I repeat, kinetic energy and the potential energy. And the Lagrangian symbol is represented by a special L that we'll see. So let us go through these equations in a very systematic way. Now see here, S0, we have taken the modified version of Maupertuis principle modified by Euler, and it is an integral mv ds, and this action integral S0, if you take a variation over that, it vanishes. So we are substituting S0. I want to show you here. This is S0 and we are taking S0 on both sides, and our principle states that it has a fixed value and that doesn't change, so its variation is 0 that we have seen in the earlier slide. And S0 I'm substituting as an integration mvds. Here velocity is the rate of change of displacement, so I want to substitute this ds as v dt. So in the next equation we are substituting ds by v dt, and here you can observe that it is mv square. Kinetic energy we define as 1 by 2 mv square. So mv square is twice the kinetic energy. So del operated on integration twice the kinetic energy dt is equal to 0. And now we shall rewrite this t in two parts. It's the same thing, but it is twice. So we have to handle it 2 times. Now total energy E is equal to potential energy plus kinetic energy. So here I am substituting T is equal to total energy minus potential energy. In this way we have taken energy and potential energy, I mean total energy and potential energy into our equation in a very elegant way. And now here we are operating variation, that is del operator, variation operator, once on T minus V and second time on energy, that is total energy. So on right hand side you can observe it is simple integration E dt. Energy is conserved, so is not changing over time, and therefore we are left with only integration dt, and integration dt will be simply t. So this del is to be operated on energy into t. Now let us go ahead with these equations, and del of et we are writing e del t plus t del e. First integration del of t minus v remains as it is, that is kinetic energy minus potential energy. This part, as I said in the beginning in this slide, we are going to write as Lagrangian, and we'll try to tackle what this represents. Now as the energy conservation suggests that the change in energy is 0, because we are talking about the situation in which energy is conserved, so we are left with only one part, E del T, and this E del T I am taking on right hand side, and here you can observe that if there is no variation in time, Now in this argument, I want to mention that we are talking about the path traced by the particle when it is sliding from A to B under the gravitational field. It takes minimum time, and that we have understood that it was a cycloid in the case we were discussing. So there is no variation in time permitted there because it is the same time path if you introduce particle at any point. In this fashion, we have reduced our equation to del operated on integration t minus v dt is equal to 0. And this is our new action, and t minus v we are calling as Lagrangian function. This Lagrangian function is T minus V, that is kinetic energy minus potential energy. So obviously potential energy is function of position coordinates and kinetic energy is p square by 2m. So it is momentum coordinates, or if you separate mass and velocity, it is you can say velocity coordinates. So in this fashion, we have finally written this equation wherein Lagrangian is t minus v. The motion of the system from time t1 to t2, this is operated over time such that the line integral, say s, is equal to integration L dt, has a stationary value for actual path of motion, where the Lagrangian L is t minus v, which is function of position and velocity and will obviously depend upon time. This is Hamiltonian principle that says about how particle moves from one point to another point on the time scale rather than talking about the path it will trace. So we are using Lagrangian, but we are talking about the Hamiltonian's principle, not Lagrange's principle. So S is equal to integration t1 to t2 t minus v dt is our action, and when we take del over that, it will vanish. This is what is the Hamiltonian's principle is in its modern form. Here we are talking about the fixed time motion of the particle, and that remains stationary and energy changes. However, we were talking earlier about the Maupertuis principle about action that talks about a path from S1 to S2. That action value we were talking in terms of S0, which is in the Euler's modified form mvds, and when we take variation over S0, it vanishes. That is a principle of least action where the energy is fixed and time can vary. You have to go back to the earlier slides and restart understanding really how Hamiltonian is talking in terms of time. Where the time is fixed, and Maupertuis is talking in terms of how it's varying on the path where the energy is fixed and time can vary. Now we shall see why it works. For that, Q of t is equal to y of t plus eta of t. In general, we can write Q is equal to y plus eta, and if we differentiate this equation with respect to time, Q dot is equal to y dot plus eta dot. So a little dot on the head of Q indicates that it is dq by dt, and this one dy by dt, and this one d eta by dt. And your action principle is del S, which has to be 0. It has to be S of Q of t minus s of y of t. So this is for the trial path and this is for the actual path. Colors I am retaining from the earlier diagram. Now, under this situation, we shall try to evaluate s of q of t, that is for trial path. It is in the Hamiltonian form as per Hamiltonian principle t minus v. Obviously it will be for t for trial path and v for trial path. Similarly, for actual path we are writing the same equation. Now let us work out t for trial path. It will be 1 by 2 mv square for trial path, and in generalized notations q we are writing by y plus eta and q dot we are writing by y dot plus eta dot. So this will be 1 by 2 m inside bracket y dot plus eta dot whole square. This will lead to 1 by 2 m first quantity square plus twice first into second quantity plus second quantity square. Similarly, t of y of t will be 1 by 2 m y dot square, and the difference will be 1 by 2 m times twice y dot eta dot plus eta dot square. Now I want to mention that this quantity is a small variation, and small variation square we shall eliminate for approximation. Similarly, V of Q, that is potential for trial path, is equal to potential Q is replaced by Y plus eta, and by Taylor series you can expand it and limit it to the first order, that will be V of Y plus eta times V dash of Y. Herein we can write the difference in V for trial path and actual path, that turns out to be eta times first derivative of space of the potential energy. And here the variation principle tells us that s of q of t minus s of y of t we can rewrite like this and simplify from these equations to this value. Herein y dot and eta dot we have to evaluate in terms of the integration by part, and then we'll simplify this equation to equate it to 0. Now for the sake of convenience I have rewritten this equation which was appearing on the last slide, and I'm considering first part of the integrand, that is m into y dot into eta dot. M is constant, does not depend on the time integral, so it is out of the integration sign, and we have y dot eta dot. Y dot means dy by dt and eta dot means d eta by dt. So product of two functions we are trying to integrate over time, integration by part. So here I want to designate this one as a first function and eta dot as a second function. So first function into integration of second minus under the sign of integration derivative of first into integration of second. Now here I want to clarify that integration eta dot is d eta by dt. So this integration is over time. So what we are doing, we are integrating a time differentiation, and that leads to simply eta. So this integration is simply eta, and that is appearing here as per the rule of integration by part. So the first component m into y dot into eta for this quantity we have seen minus m times integration, this is second time derivative of y into eta into dt. Now here this eta we have evaluated out of the integration where the limits are from t1 to t2 and it's not changing over time. So this will vanish and then we are left with minus m times integration from t1 to t2 second time derivative of y into eta dt. So what we have achieved here, I want to highlight, is this m into y dot into eta dot dt can be replaced by minus m into integration t1 to t2 y double dot eta into dt. Let's go ahead. This integration by action is equal to 0. So by action this del s is equal to 0. So this 0 is equal to this very integration which is substituted here and then minus eta times v dash, that is potential energy differentiation over space coordinate, and with this we can rewrite this equation where we have 0 on right hand side, nothing else. Now the integration of some differential equation is vanishing. The integrand is a differential equation and integration of that differential equation is vanishing. It means that integrand must be vanishing. So minus m y double dot minus v dash equal to 0. So here we have y double dot, that is second order time derivative of displacement, that can be acceleration, and this minus derivative of potential energy with the coordinate y v dash with minus sign is force. So we can rewrite that as m into y double dot is equal to minus the space derivative of potential function, rather potential energy. Therefore we can replace this m into y double dot by m into acceleration and this minus the derivative, space derivative of potential energy as force. Oh, we have arrived at force is equal to mass into acceleration, that is Newton's second law. So we have started with the action principle and we have ended up with Newton's law. So I can say that the Newton's law is equivalent of the principle of least action in a more generous way because it represents the force acting on a particle and acceleration, that is a measurable quantity involved here. So in conclusion, I would like to say that what we found is that the action is minimal for the path that satisfies the curious differential equation. Now, it might look complicated, but it's not. The derivative of the potential energy is just the force with a minus sign. And the second derivative of height, well, that's just acceleration. So if we rearrange this, we find that the path that satisfies the principle of least action is the one that obeys F equal to ma. So the Hamilton's principle of least action is the variational principle that states that the true trajectory of a system is the one that minimizes the action. The action principles lie at the heart of the fundamental physics from classical mechanics through quantum mechanics, particle physics, and general relativity. Action principles start with an energy function called Lagrangian describing the physical system. The accumulated value of this energy function between the two states of the system called the action. The action principle applied to the calculus of variation to the action. The action depends on the energy function, and the energy function depends on the position, motion, and interactions in the system. So here the action S is integration of kinetic energy minus potential energy over time. I mean integration over time dt. So Hamiltonian's principle says about how the particle moves from one point to another point rather than giving a path. The motion of the system from time t1 to t2 is such that the line integral S, which is equal to integration L dt, has a stationary value for actual path of motion, and its variation del S vanishes, that is del S is equal to 0. This Lagrangian L equal to t minus v, and therefore L depends on position coordinate, velocity coordinate, and time. So L is function of q dot t in generalized notations is a function of position and velocity coordinates and time. So we have seen that the principle of least action is equivalent to the Newton's second law, but it covers more than just mechanics. Fermat's principle of least time turned out to be nothing more than a special case of the principle of least action. So with this single principle, you could suddenly describe everything from reflection of light, refraction of light, you can say motion of a planet around a star, swinging of a pendulum, and damn anything. I hope you have enjoyed this discussion. Thank you for your attention.